Great. Thank you very much, Ian, for that very thorough introduction. I'd like to thank the organizers also for the invitation to speak here today. So I'm going to talk in two parts and cover a couple of different PV projects that are going on in my group at the moment. We're basically a materials chemistry group, focuses exclusively on solar energy conversion, and so we work on both PV as well as solar fuels topics. And the two stories that I want to tell today, just kind of highlights of some of these project areas. I'm first going to talk a little bit about our work on quantum dot photovoltaics, which was mentioned, of course, in some detail yesterday by Art Nozick. I'll have some different things to say about that topic. And then the second thing today will be on the topic of earth-abundant thin-film PV materials. And in particular, we're working on iron pyrite, FeS2, as a kind of resuscitated PV absorbing material. And I won't have any time today to talk about our work on water splitting. So you probably all recognize already that there are basically three different ways that you can take sunlight and convert it into more useful forms of energy. And really what we're talking about in this conference is the solar electric or PV approach. You can also make heat or you can make fuels. There was some talk earlier in Ian's talk about the importance of storage or the growing importance of storage. This area, solar fuels, for example, artificial photosynthesis and storing sunlight in the form of chemical bonds as like a liquid fuel or as hydrogen, is a very important and growing research area, and I think it will be the next big topic over the next couple of decades, really. PV, though, is the one that's growing the quickest at the moment, and as was mentioned, increasingly is at grid parity, so it's a very exciting time to be working in photovoltaics. So this is the famous graph from Martin Green looking at the three different PV generations. Here's the efficiency versus the module cost, and breaking PV into generation 1, generation 2, and generation 3. This is a little bit dated now, so silicon's oval is a little bit bigger, I think, these days. Of course, thin film, the two primary technologies are CAD-TEL and SIGs. And the two topics that I'll discuss today, the work that we do on Pyrite is really targeted as a generation 2 technology. So we're looking at low cost, and fairly decent efficiency, say pushing about 20% would be our goal. The other topic, the material that I'll talk about related to quantum dots, is clearly a third generation or next gen concept, where the idea is to retain the small cost but boost the efficiency, in principle above the SQ limit, the Shockley-Quasar limit of about 33.7%. And so this can be done using new kinds of photophysics, for example, multiple exton generation or hot carrier type concepts. So let me start first with quantum dots, and just a brief primer on what quantum dots are. We're talking about colloidal semiconductor dots here. So these are basically nanometer-sized crystals that have size-dependent properties. The field is very good at making homogeneous materials in a variety of different shapes, very well-controlled shape, very well-controlled size. We can make spheres, or we can cubes, tetrapods, and other kinds of shapes. And also making heterostructures. Over the last 15 years, there's been a lot of expertise growing in that area. So for example, this is a core shell quantum dot where the core is made of lead selenide and the shell is made of cadmium selenide. Because these materials are made colloidally, they're floating around in solution, and so we can use self-assembly to make thin films from them. And this is just two different snapshot images, SEM images of thin films of quantum dots on a silicon surface. Okay, so we make these materials just using normal inorganic chemistry. So this is like a Schlenk line kind of setup. And the materials come out as a two-component material where you have an inorganic core that's like lead selenide. I'll mostly talk about lead selenide and lead sulfide today. And then the shell that surrounds the core is a ligand layer that's made of usually an organic ligand, a long chain material like oleic acid, for example. Because these materials are so small, they're effectively zero-dimensional quantum objects. And so instead of having a bulk density of states that have a discrete atomic-like density of states, where you have a variety of individual discrete levels for the holes and for the electrons, okay? And you have a band gap, which is the difference in energy between those first two transitions there, or the first two energy levels. Also, because the material is so small, electrons that are contained within these quantum dots act as particle in a three-dimensional box. And so you have a particle-in-a-box type physics. And you've got energy level separations that depend inversely in some fashion on the diameter and often to the square of the diameter. So the smaller the quantum dot you make, the bluer the absorption and the bluer the emission is going to be. That's because the HOMO-LUMO gap or the band gap is larger in that case. And this is the very famous picture for cadmium selenide dots. So why would we be interested in using quantum dots in PV? There are really two reasons, and they were touched on earlier. Possibility of high efficiency, possibility of low cost. And so the enhanced device efficiency idea comes about because lots of different quantum dots have access to photophysics that suggest that you can get either larger currents or larger voltages. So for example, multiple exciton generation is the process whereby you can absorb a high energy photon, and instead of just creating a single electron hole pair at the band edge, you can make two or you could make three, okay, for example. And if you can do this process efficiently and extract out the multiple carriers, then you can, in principle, get to a device efficiency as high as 44% at 1 sun compared to the Shockley-Quasar limit of 33. So this is one motivation. You can also imagine using quantum dots for hot carrier effects as well as cheap multi-junction devices. The other approach, or the other important consideration here that's part of the motivation, is that these structures are made in solution. We can cast them using printing technology on flexible substrates, and in principle make large area materials very, very rapidly. So printing newspaper kind of idea. So this combination of high efficiency, low cost is what really motivates the field. Now you can imagine several different ways that you can incorporate quantum dots into a device, and I showed just 3 different ways here. You could make a quantum dot sensitized solar cell. You could make a bulk heterojunction by taking quantum dots and mixing them with a conducting polymer. And there are lots of groups around the world that are working on these 2 approaches. The approach that I'm going to talk about today is a kind of an all-inorganic approach where we just take a neat quantum dot film that we might call a quantum dot solid and sandwich it between 2 electrodes. And the nice thing about this approach is that it's reminiscent of normal inorganic device constructions or geometries. So we can imagine making a PN junction or a Schottky kind of solar cell. And we adopted this approach because it's all solid state. It's got a very high quantum dot loading here so that you can make fairly thin films and get all the light absorption that you want. And it has the fewest number of heterojunctions, so we don't have a liquid junction and we don't have an inorganic-organic junction. And so in some sense, we thought that this would be the simplest to start with. What do you actually need for a quantum dot solid in terms of a photovoltaic absorber layer? Well, you need all the normal things. You need to have good light absorption. You need to have a conductive thin film, so the quantum dots have to be talking to one another. You have to be able to charge separate, so you need to have some sort of built-in field, perhaps, like in a PIN structure. You need to be able to then collect those carriers in high yield, and so you need a diffusion length that's long. And in the case of quantum dot solids, we're talking about boosting the mobility and boosting the lifetime. Boosting the mobility, that means we need to couple the quantum dots very well together. We need to worry about things like charging energies that can obstruct charge transport, and we need to worry about disorder within the film. And the lifetime basically comes down in the case of quantum dots because of the very high surface area. We need to worry about surface recombination effects. And finally, we need to have long-term stability in order to have a practical kind of technology. So this is the game plan. What we're trying to do here is to make PV devices that use as their active layer a thin film of conductive quantum dots. And the idea that we need to kind of follow, or the prescription, is that we need to really gently assemble these quantum dots together in a way that does not destroy their individual quantum dot nature. So you need to retain their size, you need to retain their shape so that we keep their band gap, and also keep their ability to do multiple exciton generation intact. Okay. So we have to find chemistries and processing techniques that allow us to do things at low temperature and to do things gently to kind of keep the quantum dots as they were when we made them in solution. When I was a postdoc, I was working with Art Nozick at NREL, and we demonstrated one of the first quantum dot solid solar cells. It's a piece of glass with ITO on it, and then we have our lead selenide, in this case quantum dot film, and then a metal top contact. And this is something called a back contact Schottky device, where the electric field's at this metal semiconductor contact in the back. These initial devices were about 2% efficient, pretty high currents, so about 25 milliamps or so, very low voltages, about 0.2. If we fast forward to today, about 5 years later, 6 years later, we're talking about devices that best in field are about 7.5% efficiency. And very importantly, as Art probably mentioned yesterday, is that the NREL group in 2011 demonstrated greater than 100% external quantum efficiency due to multiple exciton generation in a quantum dot solar cell. So this effect is real and can actually be used in real devices. At this point, it's a little bit too weak to really make a big difference in terms of the efficiency, but some breakthroughs would change that. But to go from 7.5% to something like 15 to 20% efficiency is what we would really like to see to be practical technology of relevance. To do that, we need to improve some basic materials parameters. So, for example, carrier diffusion lengths are a problem right now. Controlled doping is still a major problem in the field. Junction formation, how do you make high VOC junctions? And then finally, the stability of these materials. Because we're talking about nanomaterials, there's a question about their inherent stability. And so I'm going to address these two underlined challenges in the talk today. The quantum dot PV field is only about 10 years old. It started really with Nozick's theory and sort of general discussion paper in 2002. And then you can see the progress here. This was our paper in 2008 looking at the Schottky devices. And by changing then to a PN heterojunction kind of device geometry, we can see big improvements in the efficiency. And today's Sargent's group in the University of Toronto is leading the field in terms of efficiency, somewhere around 7.5 or 8%. And this technology is now actually certified. It's on NREL's PV chart. It's, of course, way down here in the bottom. So 4 devices have been certified so far, up to 7% efficiency. And we like the slope here. The idea is, can we maintain this slope out to 20%? Right? That's the challenge. OK, so this slide looks a little bit funky, but it shouldn't interrupt my ability to tell the story here. What we do to actually make conductive quantum dot films is the following. We take lead selenide dots that have oleic acid on them. This is inherited from the syntheses. And these dots are about 5% monodispersity. They might be between 3 and like 8 nanometers in size. We take a solution of them. We make a film in some fashion by drop casting or dip coating in some way. And what we end up with is a material that you can't see it, but these should be quantum dots right here. And the idea is that the spacing between the dots is set by this long insulating ligand here, and it's significantly longer than what one would need to actually get good charge transport. And so you basically have an insulating material because the wave function overlap is essentially 0. So what we need to do to get a conductive material is to do partial or total ligand exchange and remove this oleate molecule and replace it with something else that's much shorter. In the field, people use a variety of organic ligands to do this. For example, ethane dithiol is a nice 2-carbon chain, much smaller, of course, than oleic acid is. And so that allows the quantum dots to move closer together. You get better wave function overlap, interdot distance on the order of, say, 0.1 to 1 nanometer, and you get a conducting material in that case. So in addition to ethane dithiol, benzene dithiol, and hydrazine, people these days, the main focus in the field is moving toward inorganic ligands, such as just using sulfide as a bridge between individual quantum dots. And I'll talk about sulfide a little bit later. To actually make films for devices, what we want to do is to use layer-by-layer dip coating. And this allows us to make high-quality films that give us good yields in devices. The idea is we just take a substrate, we dip it in a solution of lead selenide, and we withdraw it. That gives us a monolayer or a submonolayer of dots, but it's covered in oleic acid. We then dip that into our ligand treatment solution, in this case ethane dithiol. That strips off the oleate and allows the dots to move closer together. It also insolubilizes the dots, and so you can then just repeat this process over and over, and you can build up a thin film of whatever thickness you would like. The nice thing is that the films are very high quality. They're dense. They don't have pinholes. They're very flat, and so forth. This is a top-down view and then a cross-sectional view on a piece of ITO. So these materials, these quantum dot solids, are a new kind of granular semiconducting material. And we can understand charge transport in these materials by considering them as kind of arrays of conductive islands. These cores of the quantum dots are the conductive islands, separated by tunnel barriers, which are, the tunnel barrier has a certain width and a certain height. The width of the tunnel barrier is basically set by the interdot distance. And the height of the tunnel barrier is set by the electronic properties of whatever that material is in the matrix. In the case of our starting material, it's oleic acid. So we can tune coupling and tune charge transport in this kind of film by doing one of two things. We can either make the barrier thinner by replacing the long chain organic with a short chain molecule or inorganic ligand. And that's going to make the barrier thinner. That will enhance coupling. The other thing we can do is we can replace this organic material with an inorganic matrix, indicated by this yellow stuff here. And if we choose that inorganic matrix correctly, we can lower the barrier height without really changing the barrier width, and that will also improve coupling between the dots. And so we adopt a strategy that mixes these two approaches, and this allows us to tune coupling but also pay attention to the other factors that are important in charge transport in these films. One of those factors is disorder, including spatial disorder and energetic disorder in the film. And then the other factor that's very important is surface defects, including traps and recombination centers that can lead to loss of current. Okay, so I'll come back to that in a second. What I want to touch on briefly is the instability or stability issues related to using quantum dots, especially the lead salts in devices. So I said before that we have a number of fundamental materials challenges. We need to worry about diffusion lengths. We need to worry about making better heterojunctions, but also stability is an inherent problem. Why is it such a problem? Is because quantum dots are high surface area and high surface energy objects. And so their high surface areas make them prone to oxidation, and this is particularly problematic in the lead salts, where oxidation leads to a big change in the electronic properties. They're also, because they're high surface energy, they're metastable objects. They're little dots that want to grow into big spheres. And so they tend to sinter at very low temperatures, even less than 100 degrees C in some cases. And so we obviously need to stop that kind of stuff from happening if we're going to make a device that actually persists for any length of time. So I'll show you here some data on the poor oxidative stability of lead salt, where by salt I mean telluride, selenide, or sulfide dots. This shows a solar cell here before air exposure in red and after a very brief air exposure in blue. You just totally lose the diode. This is a field effect transistor before air exposure and after air exposure, and it's not important that we understand the details here, but you can see that you get a large change in behavior. That's not good. This was a hydrazine-treated device. That was an EDT-treated device. And then we can use ex situ TEM to look physically and see what happens to dots after long air exposures. And you can see basically that they look like they're corroded, essentially. And this is because of oxidation as well as diffusion on the material. And so we've studied the details about especially the oxidation process on EDT-treated lead selenide dots. We can use in situ gas dosing and XPS, X-ray photoelectron spectroscopy. And what we're able to find is basically the initial oxidation is due to oxygen, not to water. And so we can see a large oxygen peak that shows up. We oxidize the selenium, and we also lose the ethane dithiol molecules. They volatilize off the surface. And after long periods of air exposure, we build up a shell of lead selenite on the outside of all of the lead selenide cores. And this is going to interfere with charge transport. And so we effectively think that we have a two-stage oxidation process. In the first stage is very rapid loss of the organic molecule and absorption of the oxygen and water on the surface. This leads to heavy hole doping in lead selenide, and so we see a very large decrease in the resistance. This is before oxidation, and then immediately after oxidation, we get like a 1,000-fold change in the resistance. That's stage one, and then stage two is a much longer-term buildup of an oxide shell around all the dots that lead to a slow increase in the resistance of the film. At the same time, we can monitor resistance. We can also look at the band gap, which is just a proxy here called the first exciton energy. And we see that the band gap continually marches upward in energy. This is, again, because we build up this layer of oxides around the surface, and the effective size of the quantum dot gets smaller. And so the quantum confinement is larger, and we see a larger band gap in that case. So we can monitor the band gap just optically. So this is a major problem, not just for devices, but also for kind of basic progress in the field. People have been forced basically to use glove box technology and do experiments very quickly, and you've got always this moving target to worry about. And so we decided to solve this problem, and we've been quite successful in using a strategy of low temperature atomic layer deposition to basically completely inhibit the oxidation and the other kinds of degradation that these films suffer. So what we do is we take an insulating film, we use a ligand exchange to make a conductive film, and then we do low temperature atomic layer deposition to infill the spaces, all the interstitial spaces between the quantum dots with some sort of material like aluminum oxide, Al2O3, another oxide, or perhaps a sulfide. Okay. And by doing that, we achieve a number of things. The first thing is that we get environmental stability. So the ALD layer acts as a great gas diffusion barrier. It stops oxidation, as I'll show. It also stops internal diffusion within the film, and so it prevents the dots from sintering together at higher temperatures. The second thing that it can do is it can passivate surface states that are on the outside of all these dots. If we choose the right material, we'll passivate surface states that'll raise the mobility. And again, if we choose the right ALD material, we can decrease the barrier height. So alumina is not a good choice to do this, but other smaller gap materials are good choices. And so we built an atomic layer deposition system in our glove box to be able to do this without exposing our materials to air. If you're not familiar with ALD, it's basically a stepwise CVD approach that uses self-saturating surface reactions to make very, very nice, high-quality, conformal thin films on pretty much any surface you might want. So if you wanted to make, for example, zinc oxide, you might use diethyl zinc and water for your chemistry. And the ALD process consists of basically exposing your surface to diethyl zinc. You get a monolayer absorbing to the surface. You purge the gas out. And then you put in your water pulse. Water comes in and reacts again in a self-saturating monolayer fashion with the diethyl zinc adsorbed molecules there. You pump out the products, the side products. And what you're left with is basically a digital way to build up a zinc oxide film. And so we can prove that we, in fact, have this sort of inorganic nanocomposite where the ALD matrix has locked the nanocrystals into place and prevented their oxidation and their photothermal degradation. We can use, for example, XPS depth profile to tell for sure that we actually have a nanocomposite formed rather than just ALD kind of on the outside of the material. And so this shows here a depth profile where we've got the lead in the orange, oxygen is blue, and aluminum is in the red. And you can see that oxygen and aluminum penetrate all the way down to the base of the lead. That tells us, along with a lot of other data, that we have an infilled material here as opposed to an overcoated kind of material if we slightly change the process. This ALD infilling technique basically completely shuts down oxidation of the dots, and we can monitor oxidation again optically. If you look at oxidation of a film with no ALD treatment, then you can see that you get this blue shift effect over time with time and air. This is because the dots start out pristine, but over time they build up these oxide shells around them, and that gives us a larger gap. If you just use, in this case, 20 nanometers of alumina at, say, 27 degrees C deposition temperature, you get absolutely no change in the first exciton feature with basically months and months of storage in air. And so it's a very effective oxidation barrier. It also stops internal degradation, so what we call photothermal degradation. If you take a film of quantum dots and you expose it to UV light at an elevated temperature, 50 degrees, 100 degrees, something like that, and you do this in nitrogen, what you see is the first exciton feature is going to redshift and it's going to broaden until basically it bleeds completely into the background after some amount of time in air, or sorry, some amount of time at these conditions. So after about, say, 15 days or something like that, you've basically lost this feature. The reason that it redshifts is that you get essentially an average size increase in the dots, and the reason that you get a broadening and an eventual total washing out of the feature is because the size distribution gets very, very bad. And so essentially what's happening here is the dots are sintering and ripening with these high temperature or relatively high temperature and UV exposure conditions. We can completely prevent this by using our ALD approach, or almost completely prevent it, I should say. So this is the same kind of film, 3 nanometer lead selenide dots, and you can see in this case we have a very small redshift and basically no broadening at all. The reason that we have a small redshift in this case is because 3 nanometer dots are pretty small, and this is right on the edge of our ability to successfully infill. And so there are some regions within the film that are not well infilled, and so they ripen a little bit. Okay. If you do it with 5 nanometer dots, then the process is basically completely stopped. So we spend a lot of time trying to understand charge transport in these materials in order to try to improve the diffusion length of the minority carriers. To do this, we're often using a platform that's called a field effect transistor to measure mobility, to determine mobility. So a field effect transistor is a 3-terminal device, and basically what we're doing is we're modulating the current that flows between a source and a drain by using a gate field. And by changing the gate field, we can actually then calculate what the mobility is. It's going to be proportional to the slope of the drain current divided by this voltage on this gate field. And so we've been able to look at a number of kind of basic geometric parameters of quantum dot films and study the mobility. One thing that we've done is we've looked at mobility versus ligand length, or the interdot separation. And we did this using ligands which are alkane dithiols, and we just changed the number of carbons in the alkane chain from 2 carbons, which is ethane dithiol, out to 6 carbons, or hexane dithiol. And we can see here we've got this slope relationship. So if you look at the data, this is the drain current, this is the gate voltage. EDT, the shortest ligand, is the red, and then HDT is the longest ligand. It's down here next to the axis. And you can see that the slope gets progressively smaller and smaller as we increase the ligand size. And that's telling us basically that the mobility is getting larger and larger as we move to smaller and smaller ligands. If you plot this on a log plot, you can get a very nice linear looking slope, or really it's an exponential, for both the electrons and for the holes. So down here is basically what we call the nominal ligand length. This is effectively the distance we think that the quantum dots are separated by. And this is exactly what you would expect for tunnel type transport between quantum dots. And we can fit it to an expression and extract out the tunnel decay parameter, the wave function decay parameter. And everything fits for an alkane kind of tunnel barrier. And so we are able to use this kind of approach to tell that at room temperature, the charge transport mechanism in our film is basically sequential tunneling, where you get tunnel transport from dot to dot, 1 dot at a time. And it's phonon-assisted, meaning that we've got energy levels that are slightly different from each other from dot to dot, because we always have a finite distribution of sizes within our films. And so we have phonon-assisted tunneling is really the active mechanism. In addition to looking at ligand length, we've also looked at other basic parameters like quantum dot size and also the quantum dot size distribution. The quantum dot size, you can see, has a very large mobility dependence here. very strong, and the size distribution has a surprisingly flat dependence. We can explain both of these in terms of trap states or recombination centers within the band gap of the quantum dots, but I don't really have time to talk about that. So we use these field effect transistors. We've also applied the ALD technique to show that we can improve both the stability and the charge transport parameters. So this is a graph here that shows what happens to a film without ALD. We have very nice ambipolar conduction before air exposure. That's after air exposure, it really goes to pot. But if we use our ALD technique, in this case with EDT-treated films, this is before after ALD here, and then this is after ALD and 34 days in air. You can see basically you get some changes in the current, but the essential behavior is retained. We preserve the ambipolarity. The mobility actually improves slightly with time, just a little bit, and it makes these devices air stable over the long term. Okay, so we can actually go and study mobility now kind of on our terms. What I should have pointed out back here is that these mobility values that we're able to reach, kind of the highest mobilities that we see, are on the order of 0.1 centimeters squared per volt second. And that is not super high. Okay, so amorphous silicon can reach about 1 or 2 centimeters squared per volt second. And there's a big effort in the field right now to improve carrier diffusion lengths. So the diffusion length is really important because if we have a heterostructure or a heterojunction type of device like this, we need about a micron thick film in the quantum dot layer to absorb all the light. But of course, if we don't have large diffusion lengths, then carriers that are created back here are never going to escape from the device, and we're going to get a large hit in the current. The problem is that diffusion lengths are thought to be currently in quantum dot films about 50 nanometers. Okay? And so this is calculated basically for 10 nanosecond lifetime and 0.1 mobility. What we need to do is to get to a carrier diffusion length closer to 1,000. To do that, we could use, say, 10 nanoseconds, but we need to boost the mobility to, say, about 50 in order to achieve that kind of diffusion length. And so there's a big effort in the field right now to increase mobilities to sort of that level. And I want to show you how we can do that or get close to that using this ALD approach. So one thing that we first figured out is that by just replacing alumina with something that's smaller band gap like zinc oxide, we can increase the mobility by about a factor of 10. And so this shows before this ALD process with the zinc oxide and then after. And the electron mobility goes over 1, just a fraction over 1. The mobility increases about a factor of 15 for the electrons, and for the holes, it doesn't increase very much at all. And again, it makes the material stable. And we think what we're doing here is that it's pretty well known that zinc oxide has a very nice conduction band alignment with quantum dots, with the lead selenide quantum dots. That means that the valence band alignment is very, very bad. And so we're basically lowering the barrier to electron transport between quantum dots, but not really lowering the barrier for hole transport at all. And so this is why we believe that the electron mobility goes up and the hole mobility really doesn't change very much. So we're playing these games with other kinds of semiconductors to alter the barrier heights and thereby control the mobility. Let me show you a final way that we've been able to improve the mobility almost to 10 centimeters squared per volt second. This is by using, instead of organic ligands, we use inorganic ligands, very small inorganic ligands to couple the dots. So we take a solution of quantum dots, we do a ligand exchange, in this case with sodium sulfide, and so each of these little blue spheres here is a sulfide ion. And then we do the alumina infilling using a low temperature ALD process. And what we're able to do then is to get mobilities, depending on what the ALD deposition temperature is, we can get mobilities up to around 7 or 8 before we start seeing changes in the quantum dot sizes. And we also get very nice stability, so we can take the materials out to over a year of air exposure and there's basically no change in the mobility. So how are we getting this large mobility? Basically, we're combining the strong coupling because of this very small interdot distance due to sulfide with good surface passivation from the ALD coating. So the ALD coating comes in and it eats up traps for electrons and also for acceptor states. And so this allows us now to make basically record mobility materials that are also air stable. Okay, so very, very functional materials. And we're now trying to incorporate these into actual solar cells. So we were able to get some insight as to what's happening with this process by just looking at the field effect transistor transfer curves as a function of the number of ALD cycles. So this is 0 cycles out to 40 cycles. And what we can see is that at first the material is very heavy p-type conductor, which we can't really modulate very well with the applied gate field. That indicates that it has a high carrier density. As we increase the number of ALD cycles, we see that this carrier density falls, the current falls by quite a bit. And also we see the grow-in of an N channel. So at 20, we kind of get the beginnings of an N channel. At 25, we have an ambipolar kind of transistor. And then 30 and 40 cycles, we have a dominant N-type transistor. So we go from P channel and we tune through ambipolar to dominant N channel. And we think what's happening here is that essentially the carrier polarity change from P channel to N channel is because we're lowering the hole concentration by eating up acceptor states due to this ALD process. And we believe that the improved electron mobility is due to the fact that we're passivating some of the electron traps within the material. And we can pick this up by the dependence also on electron mobility on the temperature of the ALD process and the number of ALD cycles. So you can see that the electron mobility slightly increases here as we increase the number of ALD cycles. And so we really think that this is an effective, it's not totally effective, but it's a pretty effective way to modulate and manipulate the surface states. We can get another indication that this is happening by plotting the mobility versus the applied gate field. For most disordered semiconductors, what you see is when you change the gate field, you're basically altering the Fermi level within the material. And you can drive the Fermi level close to one of the band edges, and you're going to fill traps when you do that. And so if you look at like organic PV or organic field effect transistors, you'll see a curve that looks like this. This here is trap filling phenomena, and then finally you get to kind of a trap filled kind of mobility. And this is what our films look like before we do ALD. After we do ALD, we don't see any dependence of the mobility on the gate field. And this indicates to us that we have a fairly low trap density in these materials, very easily filled by just a small applied gate field at best. And so we can apply this technique also to solar cells. We have to do it a little bit differently than what we would use for field effect transistors. We usually use a two-step process for solar cells. We would take a conductive film. In this case, the film is selected to be a pretty low performance material and also to be very air unstable by design. We do a first step of ALD infilling, just a very thin 2 to 3 nanometer ALD infill that allows us to just alter the conduction properties of the material. We then deposit a top contact, in this case silver. The silver punches right through this very thin alumina layer to make contact with the quantum dots. And then we do a second ALD overcoating step that allows us to get air stability. This one's a thicker kind of ALD coat. And what we see in the performance is basically a doubling of the efficiency from a very low value of 1 to a slightly better value of 2%. Okay? But the main thing we were looking for is the stability. And the ALD-coated film here is totally stable out for very long times, whereas the uncoated material, you can see dies within seconds of air exposure and then kind of lives on at a very decrepit state here for a long period of time. And so by using this ALD approach, we're able to basically solve the stability problem for quantum dot materials. This allows the entire field basically to take these materials out of the glove box and do science at their own pace. And we believe it's a way that we can effectively use both for field effect transistors and for solar cells to improve hopefully both their stability and their performance, their efficiency. So with that, I'm not sure when I started, 10:20 is when we started, right? Okay. So yeah, I'm more or less on time. So with that, I'd like to switch gears now to talk about our other project, one of our other PV projects that's looking at using iron pyrite, FeS2, as a thin film absorber material. So iron pyrite, you probably know, is also called fool's gold. And so if you make a thin film of it like we've done here, it looks like this beautiful golden color. This is the team of people in my group that are working or have worked on pyrite. The idea is that pyrite FeS2 is super earth abundant, and so this is a thin film PV material that could scale very easily to very large amounts of PV deployment without ever running into cost issues due to materials limitations. It's also, of course, non-toxic. And so this is one of the main motivations for pyrite. It's been looked at in the past. It was actively researched in the 1980s and the early 90s in Germany. And I'll describe, the major problem that they encountered back then and the problem that still exists today that we're trying to tackle. So pyrite is the most abundant sulfide material in the Earth's crust. You can just buy very beautiful natural crystals from eBay that are quite large. They come out as cubes mostly in the Earth because of the cubic unit cell. It's basically a rock salt crystal structure, rock salt-like. Instead of the chlorides in rock salt, you've got sulfur dimers here, S2,2- dimers that are on the anion positions. The nice thing about pyrite is that it has all of silicon's advantages. It's earth abundant, non-toxic, and it has a band gap of around 1 electron volt, so it has almost the same Shockley-Quasar limited efficiency as silicon does. The nice thing is that it's a thin film PV material, so it's got much higher absorption coefficient. Demonstrated devices have shown very large photocurrents and high quantum efficiencies. The big thing that trips up pyrite is the voltage. This photovoltage is quite small in all devices that have been demonstrated to date. So in my group, what we try to do is make a number of different kinds of pyrite materials so we can do comparative studies in order to understand this low voltage problem. And so in my group, we work on a number of solution syntheses to pyrite, including nanocrystals and also what we call molecular inks. These are to make thin film polycrystalline pyrite materials. We also do chemical vapor deposition, so we grow it by gas phase. And we buy natural crystals, and we also make our own synthetic single crystals using a flux growth technique, which I'll describe. Just to show you a little bit about what we do with the thin film materials, this is our chemistry used for growing pyrite thin films by chemical vapor deposition. We use iron ACAC and tert-butyl disulfide. The process is at about 300 degrees C. And after we do sulfur annealing of the film to convert the material completely to pyrite, we get a morphology that looks like this from the top down and from the side. This material was actually deposited on molybdenum-coated glass, which is one of the contexts that we use for device development. And it's important with pyrite to be very careful about phase purity and also elemental purity. And so we go to great lengths to demonstrate phase purity. This is just XRD. We also use Raman spectroscopy. We use magnetic measurements. We basically throw everything we can at it, both for the phase purity and the elemental purity characterization. I'm not going to say anything more about the CVD films, except they're going to kind of leak into one of the later slides. Let me say something about what we do with the solution phase deposition. The idea behind solution deposition is to lower the costs in principle. And so we take a pyrite ink that could be a nanocrystal ink or it could be a molecular ink. And the idea is simple: deposit that onto the surface and then cook it in the presence of sulfur to get a polycrystalline pyrite layer. I'll show just very briefly two molecular ink approaches that we use. One we call the elemental ink, and this is work done by Amanda Weber. Basically, we take elemental iron, we take elemental sulfur, and we dissolve that in a simple organic solvent. And this yields like a viscous black paste that we can deposit onto a surface and cook. And so she has a certain process scheme that ends up being sulfurized in 2 steps. And this is the same kind of morphology that you would have seen for the CVD films. We can grow very nice films that are of the appropriate thickness to absorb all sunlight. And we characterize them in the same ways. And we ensure that we have phase pure pyrite to the limit of detection of all the techniques available to us. The second molecular ink approach uses iron 3 ACAC, just like the CVD chemistry did. We add sulfur to that, and we use pyridine as a solvent in this case. And this is the end result here. This is a film that's been sulfurized. So the pyrite film is very thin compared to the moly film. And actually, during the sulfurization process, some of the moly is converted to moly disulfide, and so the moly film swells by about a factor of 3 or so. And so these thin film materials, as I'll show in a minute, doesn't matter how we make them, we get pretty much all the same kinds of electrical properties. Okay. In addition to the thin film materials, we also spent a lot of time, especially in the last year or so, working on single crystal pyrite. And so we've developed a new flux growth for pyrite material. We can grow pyrite single crystals that are about 1 centimeter on a side. That's the length scale here. We can cut them up into slices and look at them by X-ray. Rocking curve shows that we have about 6 to 12 or so arc second, full width at half max. And so these crystals are about the same quality as far as XRD goes of silicon wafers. We can characterize by Raman spectroscopy. We can characterize it by synchrotron XRD to show that it is in fact phase pure. And we do full periodic table elemental analysis to find out really what's in these crystals. And we find that we've got about 160 part per million metals impurities in these crystals. So these are the biggest pyrite crystals and the purest pyrite crystals that have been made to date. The interesting thing here is to compare the electrical properties of the thin film pyrite and the single crystal pyrite. We see in conductivity plots, conductivity versus inverse temperature, 2 very different kinds of behavior. For the synthetic single crystals, what we find is that at high temperature, we have an N-type material with a large activation energy, a high mobility, and low carrier levels, like 10 to the 15 or 10 to the 16. The carrier type switches from N-type to P-type at low temperature. Okay? So this is a very uncharacteristic, strange thing for a semiconductor to do, and so we'll talk about this in a little bit. What the polycrystalline thin films look like are all, regardless of how we make them, they all look something like this. They are P-type. We have to measure the P-typeness by thermal power because the whole voltage is too small to get a carrier type out of. They have very small activation energies compared to the single crystals, and they have the opposite of the single crystals. They have low mobility and high carrier levels as opposed to high mobility and low carrier levels. And so by comparing these 2 sets of behavior, we found that we can learn a lot about what's wrong with pyrite. Okay? And the fundamental questions that we're going to ask and try to answer here is, why is the VOC low in pyrite and can it be fixed? And second of all, what is the origin of this high p-type doping that's universal in all the thin films that we make and almost all the thin films that are seen in literature? So let me first prove to you that the voltage of pyrite is actually quite a bit lower than it should be. This is the record, the champion device from 1990, actually. This is Helmut Trebuch's group, did most of the work in the 90s, in the 80s. And what you see is very large short circuit current, equivalent to what silicon can produce, but a VOC that's about 0.2 volts or less. And that's about 20% of the band gap, and really what we should be able to get out of pyrite is something between 500 or 600 millivolts. And so we've got about a factor of 3 too light in voltage here, which is, of course, killing the device efficiency. Why is the voltage low? Well, this is an area of a lot of debate, and there are a few hypotheses, and I just list several of them here. The first hypothesis is that the band gap has been overestimated, and we've looked into that in detail, and we believe that that is not the case, and so we believe the band gap, in fact, is 1 electron volt or so. The other ideas are that pyrite is never phase pure. You can argue against that just by looking at the very high EQE of some of the single crystal pyrite materials that have been made. Idea 3 is that pyrite has a sulfur vacancy defect that's present within it, either at the surface or especially in the bulk. If you pull sulfur off of one of the ion centers, normally they're octahedrally coordinated. If you pull a sulfur off, you're going to drop a molecular orbital into the band gap from the conduction band and promote one from the valence band. And so you can contaminate the band gap with these additional states. This, in principle, could lead to a low voltage because effectively you're going to have a lower band gap material if you do that. And then idea number 4 here, and this is the one that we've done the most work on and we believe the most strongly, is that there's something wrong with pyrite's surface. Either that there are surface states that are causing strange electrostatics at the surface, or the surface is non-stoichiometric and perhaps it's metallic. Okay? So the surface band gap is, for example, 0 or 0.5 volts or something. And this last idea that something's wrong with the surface has some history to it. So this is a paper by Bernold from 1994. And what these authors did is that they looked at single crystals that were N-type by Hall effect measurements. So you had a Fermi level that's close to the conduction band in the bulk. But they found that by ultraviolet photoelectron spectroscopy, the Fermi level was basically pinned at the valence band at the surface. And they invoked then this idea that in order to rectify or reconcile those two pieces of data, you've got to have band bending at the surface that's quite extreme in order to equilibrate the Fermi level here. And that's due to these surface states. And they also believe that they had sulfur vacancies present in the material. And so sulfur vacancies in the bulk are basically not ionized, but near the surface they would be ionized. And this would lead to a very sharp triangular potential barrier right at the surface that might be only a few nanometers thick. And it's a very nice situation for tunneling. And so what they believed is happening here is that most of this built-in potential, most of the band bending, is actually lost because you've got promoted carriers exploring the surface region and basically tunneling right through the top 0.5 EV of the barrier. And this is called Thermionic-field emission. It's the hybridization of field emission and thermionic emission. And if this happens, if this is really true, either direct tunneling or by trap-assisted tunneling, then you lose that 0.5. It's essentially totally lost. And then the maximum open circuit voltage that you would expect to get out is about 300 millivolts. And that is consistent then with what people are actually seeing in devices. And so the idea is that you have an N-type bulk and you have a P-type inversion layer at the surface. And so what we're doing in order to kind of explore all of these ideas and find out what's wrong with the voltage is Hall effect measurements on single crystals. And then we're going to link this back to thin film data. What you get out of a Hall effect measurement, the raw data, is conductivity and the Hall coefficient, or the Hall voltage. And I'll talk about the conductivity in a second. It looks fairly normal. We've got 3 different activation energies approximately. But the Hall coefficient, the blue data here, is pretty strange. It's N-type, so it's negative above this point here. So at this higher temperature, we have an N-type material. Then the Hall coefficient goes through 0, and then it switches sign and becomes positive at low temperatures. And again, like I mentioned, this is pretty weird behavior. So let's try to explain this. Let's first look at the conductivity. So I'm just going to extract this red curve out here. The conductivity shows 3 different activation energies. Here's the intrinsic region, where we have an activation energy of about 400 millivolts. We can model this and determine what the band gap of pyrite is from this kind of data with a lot of other supporting information. And that's what leads us to believe that the band gap is about 1 electron volt at room temperature. The second activation energy here is this orange region, which is where the material is clearly N-type. And we have an activation energy of about 150 to 200 millivolts. That tells us that we have a donor state at about twice that or so. This gives us an electron density of 10 to the 15 to 10 to the 16 with a donor density of 10 to the 18 to 10 to the 19. To explain the origin of this donor, we can use all of our elemental analysis information to rule out almost every element in the periodic table except for carbon, nitrogen, oxygen, hydrogen, and then native defects like sulfur vacancies or something else. Okay? So this donor must be one of these species here. When we're in this unipolar N-type region, we can then simplify the equation for the Hall coefficient to the unipolar simplification, and we can extract out then the mobility. And the mobility at room temperature is between 250 and 400 centimeters squared per volt second. The maximum mobility happens, it peaks at a lower temperature. It peaks to up to about 2,000 is some of the best data that we've seen so far. Okay, then we go lower in temperature here and explore this third region. Okay, so at low temperature, we get then a very shallow activation energy between 25 and 30 MeV. And the material switches to p-type. And we can see that here. Here's this Hall coefficient, N. So this is all negative here. And then it switches to P over in this region of the temperature curve. This is impossible to understand for a homogeneous semiconductor. A normal semiconductor should show a monotonic increase or change in the Hall coefficient when you're out of the intrinsic region. In order to explain a change in the Hall coefficient when you're not in the intrinsic region, you have to invoke the idea that you've got an inhomogeneous semiconductor or that you've got a change in charge transport mechanism, and so that your Hall data is no longer telling you anything that's relevant. Okay? We don't believe that the charge transport mechanism changes to something like variable range hopping. What we believe here is that this change is indicative of this idea that we've got basically a surface inversion region that's Hall type, that's Hall rich. So to model our Hall data, we use a multi-layer model that was developed by Petritz in 1958. And the idea is that we just have parallel conductivity between a surface layer and a bulk layer in our material. We can determine the Fermi level. We can just do an iterative calculation of the Fermi level with a certain number of inputs, assuming a bulk donor, certain concentration, certain ionization energy, and a surface acceptor with a certain concentration, certain ionization energy. We have to make certain assumptions about carrier mobilities in the different parts of the layer and their temperature dependence. But what we can do is actually fit this data quite well. So I show here our fit for the data that I've been showing. If we just use a bulk kind of feature with just a bulk donor, we can't fit the low temperature data at all. All we get is just monotonic changes, as you would expect. You can barely see it, but here's the fit is this dotted gray line. If we also invoke the surface acceptor idea that we have this surface inversion layer, we can fit the data quite well, especially for the Hall coefficient. And so in this particular case, the model spits out at us that we have a certain concentration for the bulk donor, certain ionization energy, and then the surface acceptor is at higher concentration at about 50 MeV ionization energy in this case. So we believe, based on this data as well as some other things that we've been doing, that we in fact very likely have a surface inversion layer in Pyrite, and that's really what's probably responsible for most of the problems that Pyrite has seen in terms of its voltage output. And so you can understand that at high temperature you've got basically the conductivity and the properties of the material governed by the band gap. Intermediate temperatures you're dominated by this donor, and at low temperatures you freeze out the donor and you've got just the surface is basically dominating the behavior of your material. If there is such a surface inversion layer in Pyrite, we should expect to be able to change it by manipulating the surface and either passivating surface states or creating more acceptors or something like this. So I show here what we call gross surface modifications, where what we've done is we've taken an as-cut sample in the red, we fine polish both sides and we get this blue data. We then grind both sides of the material with rough silicon carbide paper to intentionally damage it, and we get this green data. And then we can do a piranha etch, and that removes all the surface damage, and then we get actually improvement in the overall performance of the material in kind of the orange data. And what this shows us is that only the low temperature data is being affected by these surface modifications. All the high temperature data is not affected hardly at all. And if we assume or believe that this low temperature data is dominated by the surface, then this makes sense, right? So it's consistent that the surface is what we're changing when we modify the surface in this way, and that we're changing in some fashion the acceptor density, perhaps the thickness of the inversion layer, and that's leading to this low temperature behavior change. We can also use rocking curves to actually monitor the surface damage that we're creating, especially with the silicon carbide roughing paper. This just shows that we can in fact get very rough surfaces. We can get very, very nice and smooth surfaces down to a couple nanometers RMS roughness. And what I want to do now is tie it back finally to the thin film data. Okay, so If there's a surface inversion layer that's dominant in the single crystals, we would expect it to be even more dominant in the polycrystalline materials because they're all surface, right? You've got free surface, you've got grain boundaries. If you look at the behavior of thin film pyrite materials, this is conductivity versus temperature now, no matter how we make them, they basically fall in the same kind of behavior, right? There's a spread in the overall conductivity, but this could be due to measurement error, who knows? The important thing is that they're all curved in the same way, they have about the same activation energy. No matter whether we make them by CVD, molecular ink, or if we even look at other people's data, like made by sputtering. It's pretty much all the same. And remember, this is all P-type by thermal power, high hole concentration, low mobility. So if we have this inversion layer present in pyrite, this could very easily explain this kind of behavior, that we have all P-type characteristics and its high hole concentration. That's because if you consider what's happening at a grain boundary, if you have this sharp band bending at the surface, at the grain boundary, you're going to have the propensity for holes to sit basically at that surface site, at that the interfacial area there. And you could have hole conductivity along grain boundaries basically dominating your properties no matter what temperature you're at, okay? Because you just have so much more surface than you have bulk in the case of these polycrystalline films. And we think that this is probably quite likely what's happening. And so this inversion layer could be the universal explanation for why the single crystals behave the way they do and why people have been seeing P-type material dominating in the thin film. And also why thin film pyrite-based materials don't work, because you don't get a very good photo response at all. So how do we actually correct this and prevent this, overcome this, this surface layer? Well, one way that we're approaching this is by taking pyrite that's nominally P-type, whether it's polycrystalline or single crystalline, it doesn't matter, deposit an N-type window layer on top of it, and then do controlled thermal annealing to try to get interdiffusion across this interface and essentially destroy the pyrite surface, or alter it so drastically that we remove whatever these defects are that are causing these pinning problems and the tunneling issues. So the idea is that we want to passivate the surface states, and we also want to reduce the concentration of the subsurface defects that might be acting as islands for trap-assisted hopping or trap-assisted tunneling. And so there's our interlayer formation, and we hope that we can by doing this, we can make more high-performance kind of PN junctions with pyrite. And we've started to do this now. We take pyrite layers on moly. We deposit, for example, zinc sulfide and then a top metal contact. And we get decent rectification, but we get so far very, very little photo response. We've just started doing the controlled annealing, and so this is not after any annealing. This is just as made. So what we're trying to do in the future is to use rapid thermal processing, explore lots of different window layers, and also different kinds of pyrite materials, whether they're single crystalline or polycrystalline, and to try to get us out of this kind of potential well that pyrite has been stuck in that we think is from the surface. So with that, let me thank all the students that have worked on these projects in my group, as well as our collaborators at UCI that are involved mostly in the pyrite research, and our collaborators at NREL and Los Alamos that are involved in the quantum dot research. I also need to thank Jeff Lindemuth at Lakeshore for help with some of the Hall measurements on pyrite. And I need to thank NSF for support, as well as DOE, both the EFRC program that supports our quantum dot research. This is called the Center for Advanced Solar Photophysics that's run out of Los Alamos and NREL. And the DOE for support of our pyrite research from the Sunshot program. So I'll just leave this list of conclusions up, and I'd be happy to take any questions that you might have. Thank you very much.